Okay, so in this video what we're going to do is introduce you to a very important mathematical constant that was first really discovered and worked with by Jacob Bernoulli in the late 17th century. Okay, and his interest really came from working with compound interest. And the idea is that, let's say that there is a bank and you're going to invest £1 in the bank, okay, and the bank is offering 100% interest rate. Now, we use this idea of working with a bank just to kind of help the idea along. Now, obviously 100% interest rate is a bit far away from what we would expect banks to give us. But that's not to say that 100% interest rate doesn't actually exist in real life when we're thinking about population growth, for example. Okay, so it's not an idea that we can just discard as not having any merit. So let's say that the bank has offered us 100% interest rate over a year. Okay, so what happens is that your £1 gets invested in the bank, and then at the end of the year you would receive £2. Okay, because you've gained this 100% interest. Now, what would happen if, instead of the bank just giving you your interest at the end of the year, okay, what if that interest, the 100%, could be split up over 2 6-month periods, for example? Okay, so instead of earning 100% at the end of the year, you would earn 50% on your money in the first half of the year and 50% in the second half. Okay, so your £1 that you're investing would go up to £1.50 after 6 months. Okay, and then at the end of the year, after another 6 months, you're going to earn 100% on top of this. Okay, 50% on top of the 150. Now, 50% of the 150 is 75p. Okay, and so you would be up to £2.25. Okay, so what's going on here is the way of writing compound interest so that we've got this £1 being multiplied by, well, we need the 1, okay, to say, right, we've still got 1 of the pounds plus the amount of interest that we've got. So in this case, it was the 1, okay, 100% interest, which could be represented as a decimal as 1. And that was happening once. And so this is where we get this 2. Now, for this second example, I've got this £1. Now, we've got the 1 original, but now, okay, if we think about what the actual interest rate was, it's 50% over two sections of the year. Okay, so we're actually getting 50% in the 6 months, first 6 months, 50% in the second 6 months. Okay, and that's happening twice, and that's where we're getting this 2.25. Okay, so 1 plus a half squared. So now, if we continue this concept, okay, because it appears that we're earning more if we're subdividing the year into smaller categories. So let's say we split it up into 12 months of the year. So actually the interest was calculated every month. So we'd have the £1 invested. Now the 100% is going to be divided up into 12, so you're getting 1/12 interest every month. And that's going to happen 12 times. So we've got 1 plus 1/12 to the power of 12. And that gets us 2.613033529. Okay? So I'd be up to £2.61. So that's obviously better than my previous idea. So if we go from 12 months, well, let's say now we go to weeks. So 52 weeks in a year. This would be our formula. So 1 plus 1 over 52 to the power of 52. And that's 2.6925969954. So what you can now start to see is that although I'm subdividing the year up into smaller and smaller pieces, the actual amount that I'm gaining from doing that isn't actually increasing as much as it was previously. Because I'm now up to £2.69, okay? So it's about 8p more than I would have done if I'm getting it every month. So let's see what happens if we calculate it up to daily. Okay, so £1, 365 days in a year. Okay, so 1 plus 1 over 365 to the power of 365, and that gets us 2.71456748.2. Okay, so what if we earned a bit more? A couple of pence. Okay, so even though 52 has increased quite dramatically to 365, it hasn't made that much difference, this number that we're getting at the end. Okay, so let's try one last example. Let's try one more. How many intervals should we divide the year up to? Well, let's choose 1,000,000. So 1 plus 1 over 1,000,000 to the power of 1,000,000. And that's 2.718280469. Okay, so even though we've increased this number dramatically, the actual number that we're getting here hasn't changed a great deal. Okay, and you can see that it does seem to be homing in on a particular value. And that value is this mathematical constant that I was talking about. Okay, we actually call this number E. And you can see that it is coming from something that's quite a simple idea, but is actually evolving from that idea to become something that's actually very important. And it's coming into exponential growth and then exponential decay. Okay, so things that grow exponentially or decay exponentially, like radiation, for example. Or you could look at how population changes. Okay, so that is why this number is so important. And we can generalize this. So what we're doing is we're increasing this number. So 1 plus, let's represent that number with n. Okay, so 1 plus 1 over n to the n. And what we say is that n is getting larger and larger and larger. So we say that the limit as n tends to infinity, okay, is E, this number E. Now the number E you should be able to find on a calculator as well. Okay, so on the Casio FX991EX, it's above the LN button, so Shift E, and then you can type in 1, E to the 1. Okay, so E to the 1 is 2.7182812828, etc. So we're actually very close here. So that is where the number E can be found. And there are a number of other derivations to get to E as well, okay, that is definitely worth exploring. But it's important to know how important this number is, okay. It's up there with pi in how we continue with it into higher levels of mathematics.